So let's start, this is a continuation of the linear algebra review. Let's start this one with null space, or also known as kernel of a matrix. So this will be the collection of vectors that get killed by the matrix. So for example, with those smiley face transformations I was showing, the rotation and the shear, these two matrices, those would not kill anything other than 0. So those have what you would call a trivial null space. And you can tell that from the picture because nothing was sort of getting crushed and losing volume, losing its dimension. Or in the case of the smiley face, it has area. It wasn't losing its area. Okay, but let's be a little bit less vague about that. It's the collection of vectors that get killed. We always know that 0 gets killed. So the null space of a matrix is never the empty set. It always contains at least 0. The question often is, are there any others? So if the null space contains only 0, then we say it's trivial. And if there are other non-zero vectors in the null space, then we say it's non-trivial. So to say that something is in the null space, so let's say I say A times 2, 3, or how about this? Let's say I have this matrix, 1, 2, 3, 4, and I say V1, V2 is in the null space. That means this is true, right? If I say that this is in the null space, that means this is true. That means this is true. Just doing out the matrix multiplication on the left side. It's just taking a linear combination of these with these coefficients, used as the coefficients. So to say that this vector is in the null space of this matrix is to say that this is true. But this can only be true for non-zero V1 and V2 if these vectors are linearly dependent. So you see, having or not having something in the null space of a matrix is very closely related to the question of linear independence or dependence of the columns. So if the null space of A is non-trivial, then that means there is some non-zero vector, let's say V1, V2, in it. And instead of A, let me make it a little bit more explicit. How about A, B, C, D? Let's just stick with 2 by 2 matrices. If the null space of A, B, C, D is non-trivial, then there's some non-zero V1, V2. Non-zero meaning not both of these are 0, right? When we say a vector is 0, we're saying all entries are 0. When we say a vector is non-zero, we're saying maybe some entries are 0, but at least one of them is not 0. And to say that the null space is non-trivial is to say that there's some non-zero vector such that when you apply this matrix to this vector, which yields this, V1AC plus V2BD, that gives you 0, right? But this is the same. It's the same as saying that the vectors AC and BD, the columns of the matrix, are linearly dependent. And it goes the other way. To say that the columns are linearly independent is to say that the null space is trivial, that it only contains that which it must contain, namely 0 itself. Often one thing we want to do with matrices is invert them. So let's say you have a 2 by 2 matrix A. Let's say it's a square matrix. This is a square matrix. So maybe 2 by 2, maybe 3 by 3, whatever. Can we invert it? So what is meant by inverting? Like, what is meant by A inverse? It means undo what A does. So like if A is a 90-degree rotation this way, then A inverse will be 90-degree rotation the other way to undo that. If A is a shear that does one thing, then A inverse will be a shear sort of the other way that just puts all the points back where they were supposed to be. You can only invert matrices sometimes. So let's look at what might prevent matrices from being invertible. So first of all, if we were able to invert a matrix, if A did have an inverse, so if there were a matrix worthy of being called the inverse of A, then it should be that if I apply A inverse to A applied to a vector, then that should give me the vector back, right? That's the whole point. if I do A to a vector, then A inverse should undo that and get me back to the original vector. So if A could be inverted, then this should work, right? But suppose A has a non-trivial null space. Suppose that. So say V is in the null space. And V is not 0. That's what makes the null space non-trivial, that there's something other than 0. We always know 0 is in there, but we're assuming there's something other than 0 in there. So V is not the 0 vector. Then, look at this. The left-hand side, so let me just talk through this instead of writing. Just look at this. The left-hand side would be, here I would have A times V, which would be 0, right? The 0 vector. And then what's A inverse applied to the 0 vector? It doesn't matter what A inverse is. If you take a matrix and you apply it to the 0 vector, you will get 0, so you get 0 here. Ah, but then V is 0, after all. Okay, so it only makes sense to have, this is nonsense, right? So it only makes sense really to have something called A inverse. It will only possibly work if A has a trivial null space. So a non-trivial null space is an immediate indication that A cannot be inverted. You cannot undo what it does. And it turns out that having a trivial null space turns out to also be enough to make a matrix invertible. So if you have a square matrix, then it's invertible if and only if its null space is trivial. It does have to be a square matrix. So this is one of these things that you study in linear algebra, that trivial null space is sufficient actually to make a matrix be invertible, for sure. Okay, so it would be nice if we had some way of determining whether the null space of a matrix is trivial or not. There are ways, of course, just using the idea of null space, using the definition of null space, and just trying to look at this linear system, this applied to vector equals 0, and then seeing what solutions there are. Can I find non-zero solutions? Can I prove that these have to be 0 in this situation? You can do that, but there's a quick computational way to do it, which is actually not so quick when the matrices get large. It's actually kind of useless, but there is a quick way for small matrices to immediately know whether null space is trivial, and that's the determinant. So the determinant of a square matrix is going to be non-zero if and only if the null space of the matrix is trivial. So let me give you an example of a matrix that has a non-trivial null space and therefore 0 determinant, this one. And you can probably, if you pause and just stare at this for a second, you can guess how I came up with this example. It's really stupid. I just picked something for the first column, something mildly interesting looking, and then I just doubled it for the second column. Obviously, the two columns will then be linearly dependent, right? One is a scalar multiple of the other. So the determinant should come out in 0, and if you compute the determinant of this is 1 times 4 minus 2 times 2. So I get 4 minus 4 is 0. So non-trivial null space. Not invertible. This matrix cannot be inverted. Let's figure out what the null space is and try to describe it actually. So how about this first actually? Let's apply this to the smiley face and see what happens. Okay, it turns out I closed Inkscape and lost the previous smiley face. So here's a new one. And we're going to apply this matrix 1, 2, 2, 4 to it and see what happens. So take this, apply the matrix. Oh, that's interesting. Look at that. It's not doing anything, but it's giving me a message down here. The message disappears. Okay, when I mouse over it, the message disappears. But yeah, there it is. I don't know why the message keeps changing, but look here when I click on apply. The transform matrix is singular, not used. Okay, that's reasonable, I guess. It doesn't want to just crush everything. Basically, this would crush everything. How about I try something that's not quite determinate 0, but close to it. So instead of 4 here, I'll put 3.999. There you go. See, I don't know if this is even showing up in the video. It's such a thin line. How about not so close, 3.9, and I apply this. You see that? It just got totally smashed. And you can imagine if I put in 4 here, then it's just going to get smashed onto a perfect exact line. Yeah, I was curious how it would react to a singular matrix. So can you recover? Can you undo that? Like if I'm just doing like this, sorry. If I'm just doing like some random matrix like this one, you can imagine undoing this, right? You can imagine like trying to take the smiley face and stretching it and putting it back together. But if I did this, except even more, if I actually put 4 here and put in an actual determinate 0 matrix, there's no way you're going to put the pieces back together. You can't even see the pieces, right? The eyes and the mouth have been lost. It's just a line now. So I think of a singular matrix or a determinate 0 matrix or a matrix with a non-trivial null space as one that loses information. It actually destroys some information when you apply it to things. It cuts down on the dimensionality of things. It used to be that the smiley face had area, and then after applying it, it only has length left over. It has no area. Okay, for fun, let's try to describe the null space here. Exactly what are the vectors that get killed? So let's see. Basically, I'm trying to solve this linear system where I put let's put coefficients C1, C2, and I want to see which choices of vector C1, C2 here are going to give me 0 at the end. Actually, I was using V1, V2 before, so let me continue with that notation. Okay, so probably you learned this technique in Math 4a where you write an augmented matrix. You put your right-hand side here, you put a line there, and then you apply the rules of Gaussian elimination or row reduction or whatever. There are some rules that you can apply to this matrix that basically preserve what the solution set is going to be. And then you try to strategically apply the rules to reduce this down to a situation where it's obvious what the solution set is. So we can go ahead and do that. Here's the result of the first step. I have subtracted twice of the first row from the second row, and big surprise, I got 0 for a row. That's actually not too surprising. That's what you're going to end up with when you have a singular matrix. And now I'm left with one equation. I just have to deal with that equation. So what's the equation? V1 plus 2V2 equals 0. That's the equation. And of course I can't just solve this and figure out exactly what V1 and V2 must be. That's because there's not just one solution, right? So I need to choose one of them to leave as a free parameter to help me describe my set of solutions, and then use that to say what the other one has to be. So let me just solve for V1, since that's easy and doesn't require me to divide by 2. And how about I just say V2 is the free parameter then, and then here's V1 described in terms of V2. So then what are the vectors V1, V2 that work, that get killed by this matrix? They're all the vectors that look like, that have V1, their V1 position being -2 of their V2 position. So these kinds of vectors. Here's another way to describe it. V2 times -2, 1, this vector. So this direction is the direction that gets killed, and any scalar multiple of that, anything along that direction, is going to get killed. So, often we prefer to write vectors using the standard basis, like 1, 0, 0, 1, like I was showing you back here when we were talking about this. 1, 0, 0, 1 is a great basis. But if you look at this the matrix here, 1, 2, 2, 4, there's this particular direction that it just seems to kill, right? If you apply this matrix 1, 2, 2, 4 to the vector -2, 1, or anything along the direction of that vector, so any scalar multiple of it, then it just kills it. So maybe a good way to understand what this matrix is doing is, instead of writing vectors out in terms of their x and their y component, or their like 1, 0, 0, 1 basis representation, instead you might want to write vectors in terms of their component along this direction and then their component along some other direction. Since we know that this matrix will just kill the component of vectors along this direction. So this is actually something we will be doing a lot when we're working with our linear systems of differential equations, is we'll take the matrix of coefficients and be like, okay, maybe there's a better basis than the standard basis that we can use to understand how it's operating. If there's a direction that it's just killing, then it would be good if we incorporated that direction as one of our coordinate directions. In other words, when you draw your coordinate axis, instead of just going ahead and making the y go vertical and the x go horizontal, maybe choose your axes to go along directions that are more useful for describing that particular situation. So the way to actually do that, a systematic way to do that for different matrices, is to solve the eigenvalue problem for a matrix. So we will have to become familiar with doing that. Okay, so there will be another linear algebra review a little bit later on. For now, for the next lecture, or possibly the next couple of lectures, I'll go back and focus on the differential equations material. Then when we start needing the eigenvalue theory stuff, then I'll do another linear algebra review for the sake of that.